So, we're now going to look at graphs of motion. And this is just graphs in general, and we're going to look at some shapes, and then later in Unit 9, we'll look about how we apply what we've just learned. So, we've discussed some things, and we've discussed how we can calculate some motion because we know average speed, average velocity, all of those nice things. But we can also show how an object moves by looking at a graph. Graphs are actually very useful for us. So there's three main types of graphs of motion: displacement versus time, or position versus time. So we're looking at the meters, okay? Velocity versus time, and then acceleration versus time. So those are the three main ones that we do, and all three of these can tell me quite a bit about how my object's moving, okay? So, number one, a graph consists of a y-axis, which is the vertical axis, and that's the dependent variable. It's the thing we're measuring. So in this case, it's going to be acceleration, velocity, or displacement. Then we've got the y-axis, which is the independent variable, and that's, in this case, time. It's the thing we control. So, that's what I've said there for you. Signs are very, very important with these graphs, okay? And remember, like we've done before, you have to choose a direction as positive and stick to it. Sometimes, though, if I give you a graph, or you're given a graph, the graph tells you and explains to you exactly what is your positive direction, and then you don't actually have a choice. You must use that direction. So, if we have uniform velocity, uniform means constant. The position changes constantly, but it changes at a constant rate. So if I say the velocity is 1 meter per second, that means every second for the whole motion, this object's going to move 1 meter at a time. The object does not accelerate. Acceleration is 0. That's why the velocity is constant, okay? Now, what that means for us is that displacement and velocity gives me a straight line, okay? So if this was 1 second, that would be 1 meter. If that was 2 seconds, then that would be 2 meters. That x is just a random position on my graph, but it changes by the same amount every time. It's always a straight line then. It's got a constant positive gradient, which means velocity is positive, and gradient is the same as gradient in maths. We can find if we find the gradient, it gives us the velocity. Remember in maths that gradient is your change in y value, y2 minus y1, over your x value, x2 minus x1. In this case, y happens to be displacement. Displacement is an x. X is time, and time is a t, which is why we can say change in the y value over change in the time value. That gives me a velocity. So that's quite useful. Because my velocity is constant, it's a straight line parallel to the time axis because it's not changing. Okay, and it has a value, so it's a nice straight line. The gradient is 0 though, because acceleration is 0. It's in the positive direction of motion because it's on the positive side of my axis. And it's above the time axis. If it was a negative, velocity would be below the time axis. Velocity is constant. Velocity time graphs are actually very useful because the area under the graph, and by area I mean this little part, gives me displacement. So just quickly, we know velocity is change in displacement over change in time. So to get displacement on its own, it's velocity times time. Velocity happens to be my y-axis, time is my x-axis, and now I've got an area because I'm going length times breadth, okay? Just a reminder that the area of a triangle is a half base times height. Very, very important. So, the gradient, we just saw it with the last graph. The gradient gives me acceleration. Okay? The acceleration time graph, now you need to make sure I can see that line. There's no acceleration. So acceleration is 0, which means it's on the time axis and it's a straight line. We pretty much are always going to have acceleration as a straight line because we work with constant motion. We are working with linear motion, okay? So a car moves at a constant velocity in an easterly direction. So now we're going to draw some sketch graphs. What you need to remember about sketch graphs is we do not need a heading, okay? So we're going to draw a sketch graph. We don't need a heading. We must label axes, okay? And we must with units. And what we're looking here, it's not to scale. Okay, so it's not to scale. I'll pretend you guys can read what I'm writing. It's not to scale, but it's to show me shape. Okay, that's what I'm testing when I ask you to give me a sketch graph. So, the displacement time graph is a straight line, because all I said to you was, it's moving constant velocity, easterly direction. Constant velocity, straight line delta x. Velocity, straight line across the parallel to the x-axis. And then the acceleration time graph, well, there it is. Nice and straightforward. But what happens if there's uniform acceleration? Uniform acceleration means there's a constant acceleration, so your velocity is constantly changing. There's an increasing amount of distance covered in equal time intervals. So if I'm saying it's accelerating at 1 meter per second squared, it means in the first second it's going at 1 meter per second. In the second second it's now going at 2 meters per second. Then it'll be going at 3, etc. So every second it's going to cover a bigger distance. This is very important. Acceleration, it accelerates positively if the acceleration and the velocity are in the same direction and the velocity increases. Okay, that gives me a positive acceleration. So here we look at this and we go, and you can do this by working out values. But it's a curve because every second it must cover a bigger time interval. Must be bigger here because it's getting faster. Okay, it's a parabola. You don't need to worry about being able to do the equation of a parabola. It's not going to get asked. It's a positive gradient which increases. This gradient's getting steeper and steeper and steeper. Why? Because it's getting faster. Remember, I said to you in the just now that if I could find the gradient of this graph, this gradient would still give me the velocity. Okay? But this velocity is always changing, which we know. Why? Because it's accelerating. If we now look at velocity, velocity is going to give me a straight line because every second it's getting faster by the same amount. We're only working with straight lines for velocity. The gradient is positive because acceleration is positive. Okay? The direction is motion is positive because it's above the x-axis. And it's a straight line because it's got constant acceleration. That is a constant value. Positive constant acceleration. Again, just like I said to you, the area under the graph gives me the displacement. So the area here would be a triangle. So it's a half base times height. The gradient gives me acceleration, which will give me a positive value. All right? Now, acceleration is a straight line. Has to be because we're using constant acceleration. Very important. So we've spoken about all of that. For example, now in your notes, please change these values for me because they are different to the ones that are on the printed notes. An object moves from rest. The table below, and take this out because it's not going to help you, records the object's displacement during its motion. Okay? So after 1 second, it's going at 0.5 meters per second and the displacement is 2. Okay, etc. They want the results to draw the following. Now, I'm asking you to draw it using, this is an accurate graph now because you've got values. So what I need you to do is pause the video, quickly draw for me the displacement time graph and the velocity time graph, okay? Once you've done that, then come back to the video. Okay, start it again. So, number 1, you're going to get a curve for your displacement time graph. And it's a bit harder to see, but that's okay. Number 2, you should have got a nice straight line. Now, yours is going to be slightly different to mine because of the values. Don't worry. The thing that I wanted is that it's straight line and we're all happy. Okay, and in fact, what should have happened is that this is at 0.5. This is actually at 1. I know my values don't quite work. The 3 was at 1.5. Oh, this is terrible. And the 4 was at 2. Okay. When we draw the acceleration time graph, this is now a sketch. I haven't worked out the acceleration. So acceleration is just a straight line at a value. I don't know this value. I haven't worked it out. They want you to describe the motion. Well, this motion is constant positive acceleration. All right? And it's for 4 seconds. Is that how much it was? Let's just go check quickly. 4 seconds. Let's see. Yep, for 4 seconds, okay? So that's quite straightforward. Now they want us to use the velocity time graph to calculate the acceleration. So we go back here, and I want the acceleration. Acceleration is the gradient of this graph. So I'm going to use the last point that I know, and I'm going to use the origin, because that's the easiest way to do this, okay? So the gradient is change in velocity over change in time. I'm using the point 0, 0, the origin, and I'm using the point 4 seconds, 2 meters, okay? So that means it's going to be final minus initial, final minus initial, y1, y2 minus y1, final minus initial, okay? So that means my acceleration is 2 over 2, which is 1 meter per second squared forward. I didn't say what direction I was going in. Okay, don't worry about all of that. Constant negative acceleration, we have smaller distances in equal time intervals. The velocity gets smaller. The acceleration is negative. So if my velocity is positive, my acceleration is negative. My graph slows down. So now as we look at this, the gradient gets less and less steep. Less and less steep. So it's been going from, say, 3 meters per second to 2 meters per second to 1 meter per second. So every second it's covering 1 meter less than the second before. It's a parabola. It's got a decreasing gradient and it's slowing down. Your velocity now goes from a big velocity to maybe 0, maybe not. It depends on the question. Okay, but if it goes to 0, obviously it has stopped. And then you can see this is a negative gradient. And just like all before, you get the gradient to give you the acceleration. So, acceleration now is below the graph. It's a minus value, and that's okay. That minus value is simply telling me that it's slowing down. That's all it is. So, here we have a racing car that is slowing down. At 1 second, it's going 150 kilometers per hour. 2 seconds, 100. At 3 seconds, it's 50. And at 4 seconds, it has finally stopped. If we draw a sketch graph, which means I don't need you to give me any values, the sketch graph is going to show me, alright, said that, it's going to slow down, okay, and eventually, so at 4 seconds, my graph is done, okay, it's not going to go anywhere else, we're not going to worry about that, okay. Your velocity time graph, now here I've got meters per second, but they did give it to me in kilometers per hour, but we would usually draw it in meters per second, unless I tell you otherwise. So technically, this really should be kilometers, and this should be kilometers per hour, but right now, I'm really wanting you to see the shape. Okay, it had a velocity, and then it stops. The acceleration is below the graph. So that's 0. It's negative acceleration because it's slowed down. And over here, that would be 4 seconds. Okay, we're going to stop there for this unit. Once you're happy with this unit, you can go on to Unit 9.